Mathematical treatment of LC oscillation. Okay, this is a capacitor which is having a capacitance C, and it is connected to an inductor having an inductance L. Okay, so we have seen right before that when this charge capacitor is connected to the inductor, then there is a transfer of charge from capacitor to the inductor. So in that process, right, an EMF is induced in the inductor. Okay, and that induced EMF, it will be opposite to the EMF which is present in the capacitor. Okay, suppose initially, let's say this capacitor contain a charge Q naught initially, that is when the time is equals to 0. When the time is 0, that means when you are not connecting the capacitor to the inductor, right, the charge in the capacitor is Q naught. Okay, then what happened here is when you connect the capacitor to the inductor, then the charge will start moving through the inductor. Suppose at a time t, let's say the charge left in the capacitor, let's say it is Q. Okay, what is the charge left after a time t when you connect the capacitor to the inductor? Let's say the charge is small q. Okay, now what happens here is this. The potential drop across the capacitor and the inductor at every instant of time, it is always the same. Okay, which means potential drop across C is always equals to potential drop across L at every instant of time. So that is, if you remember, this potential drop, it can be written in terms of capacitance as Q upon V, because Q upon C, because we know V is equals to Q upon C. So this is the potential drop across the capacitor at a time t, because the charge is Q at a time t. And what is the potential drop across the inductor at a time t? That potential drop here, it is nothing but it is the induced EMF. Okay, so that induced EMF, it is minus L di upon dt. Okay, so what is I? I is actually the current which is passing through the inductor at a time t. Let's say the current at a time t, it is I. Okay, so this is the induced EMF. I hope you still remember this equation. So this EMF, this induced EMF, it is like a potential drop only across the capacitor. Okay, so if this is the case, then I can say that taking this to the left, you'll get L di upon dt plus Q upon C is equals to 0. Or you can say di upon dt plus, if you divide both sides of the equations by L, then this will disappear, and here you'll get, okay, you'll write Q upon LC, and when you divide the right hand side by L, you'll get 0, isn't it? Okay, now if you further write this equation, I can say this is ddt, and what is I? I is the current at a time t, which means the instantaneous current. So for the instantaneous current, we write dq upon dt. Okay, so therefore instead of I, I'll write dq upon dt plus q upon LC is equals to 0. Or this is equivalent to dq, it means d2q, dt means dt square, plus I will write 1 upon LC in this way, times q is equals to 0. Okay, or I can say d2q upon dt2 plus, now instead of 1 upon LC, I can write omega square times q equal 0. Okay, so this is the equation. I'll name this as equation 1. How much is omega in this case? This omega here is equals to 1 upon root LC. Okay, right? I think you still remember this equation also when we talk about resonance, right? When you go back to the resonance topic, then you'll get omega is equals to this much. Okay. Now, this equation 1, it is known as a second order differential equation. For this you will do in BSc, I think, or maybe you have done it in class 12, I don't know, because I'm not taking mathematics. But to every equation we always have a solution. And the solution of this type of equation, right? The solution of this equation 1, it is in this form. Q, because here the variable is Q, so I'll write Q is equals to, like in this form, A cos omega t plus B sine omega t. So this is the solution of this equation 1, where A and B here, they are constant, and the value of A and B can be found from the initial condition. Okay, so this is my equation 2. This is my equation 2. So let us find out how much is A, how much is B using the initial condition. Okay, so when I say initial condition, it means when the time t equals 0. When the time t equals 0, what is the charge in the capacitor at that time? Q naught. Q is equals to Q naught. Okay, so if you substitute this value of t and q in this equation 2, so I can see your equation 2 becomes Q, instead of Q I'll write Q naught. This is A cos omega t. T is 0, so omega into 0 will be 0, plus B sine t is how much in this case? 0, so sine 0 will be 0. So that means this term will disappear. Okay, or I can say that Q naught is equals to A, because cos 0 is 1, isn't it? Cos 0 is 1, so 1 times A will be A, so Q naught is equals to A. Okay, now I have found just A. Now what is B? For B, okay, I will do like this. If you take the current I, you know the current is equals to dq upon dt, isn't it? Or, but Q, how much is Q? Q is this much. So when I say dq upon dt, it means you have to differentiate, this whole thing here. So when you differentiate A cos omega t, you will get minus omega A sine omega t. And when you differentiate B sine omega t, you will get omega B cos omega t. So now I will take common this omega. Okay, if we take common this omega, then, or else I'll just simply substitute the initial condition only. So at t equals 0 again, at t equals 0, the current is how much at the time? When the time is 0, the current is 0. Okay, so when I is 0, then I'll write 0 here, and this is sine, because we have t here, so t is 0, so sine omega into 0 will be 0, so sine 0 will be 0, so everything will be 0, that means this term will disappear. Now we have omega, and here, okay, B, since at t equals 0, when you put t equals 0, you'll get cos 0. Cos 0 is 1, so you'll get like this. So omega b into 1 will be omega b, but when you find out b from here, taking omega down, you'll get 0. So we have finally found the constant A and B, where A is how much? Equals to Q naught, and B is how much? Equals to B naught. Okay, so if you substitute the constant A and B in this equation 2, then you will get like this. Okay, from equation 2, Q is how much? A. A is how much? A is equals to Q naught, and then cos omega t, plus B, but B is how much? 0, so 0 times anything will be 0. So this is the equation for the charge at an instance of time t. So this is the charge. Okay, now let us look at the current. We know current is written as dq upon dt, which means you have to differentiate ddt of q naught cos omega t. Or the instantaneous current, it will be, this q naught is constant, I'll take it out. So when you differentiate cos omega t, you'll get minus omega sine omega t. Okay, so this is the equations of current. Okay, so this is, I'll name this, what is the last equation, number 1. So number 2, I'll name this as equation 3. This is equation 4. So looking at these two, equation 3 and equation 4, I conclude that this charge, which is oscillating between the capacitor and the inductor, right, it is varying sinusoidally or cosinusoidally, because of course, so I can say cosinusoidally. And this current here, because of the presence of this sine omega t, I can say the current which is flowing in the circuit, it varies sinusoidally with time. So, okay, the maximum value of charge in the capacitor is Q naught, and the maximum value of current, what is the maximum value of current? For current to be maximum, let me denote by I naught, and this I naught will be how much? I naught, right? It will be maximum when this sign is maximum. When sign is maximum, it means this quantity should be equals to 1, because maximum value of sign is 1. So when this is 1, so you'll get only just minus Q naught omega. Okay, Q naught omega. Or I'll just write only Q naught omega without writing the negative sign. Right? Because negative sign, it tells you only the direction, but only magnitude. This is the maximum value of the current in the circuit. Okay. Now the maximum value of current in the circuit, in this case, it will, oscillate with a frequency f is equals to 1 upon 2 pi root LC. So this current, which is actually flowing in this circuit, it will be having this frequency, and this frequency is maximum, right, when the current in the circuit is maximum, right? I think you still remember when we talk about resonant condition. So in the resonant condition, right, in the resonant curve, we have seen the current is maximum at this frequency. Okay, similarly, the charge will be maximum at this frequency. Okay, so both current and electric charge are oscillating with this frequency. So because of this nature of equation, when you plot the graph of electric charge and current, you will get like this. Suppose this is a time, I'm taking, suppose, a current, right? So this current, because it varies sinusoidally with time, so you'll get a current like this type. And a charge also, right, because of this cos, so starting from this point, I'll get, this is the graph for the charge. Okay, so, right, this is about the mathematical treatment of LC oscillation.